if you have this kind of graph, okay, and they ask you to discuss about this graph, for example, okay, discuss about the boiling point, okay, related to this graph, okay, and then they give you 3 marks for this, okay, 3 marks for this, okay. I'll give you 10 seconds, okay, please think. What are the points, okay, that you might want to include, okay, to discuss about this graph? 3 points. Okay, let's start. Okay, Wilson, I will jot down over here at the side. So if they ask you to discuss, what are the points that you think will be suitable that you need to discuss over here, Wilson?
Polarity.
Okay, you mentioned about polarity. So to be exact, regarding polarity, what are you going to actually discuss about polarity? Polarity of what?
The attraction between negative and positive.
Okay, I know. But since they mentioned about this polarity, right? So you're telling that, okay, you want to discuss about whether these molecules are they polar or not. Okay, so maybe that is your idea. So tell me now, okay, are we talking about polar molecules or non-polar molecules?
Polar.
Okay, we are talking about polar molecules. Okay, polar over here. Now, if you look at the trend of the graph, okay, what can you say about the trend of the graph? Let's say I'll ask someone else. Owen. Owen, what can you say about the trend of the graph?
It rises from HCl.
Okay, it rises from ACL. Good. Okay, it rises from ACL. But for HF, that is unusually like very high boiling point. Okay, for HF. Okay, so that is actually you're talking about trend. Okay, so basically I have like 2 points roughly. Okay, 2 points over here. So maybe the trend, apart from the trend, okay, I think you still need to discuss about HF. Okay, Thompson, what are you going to discuss about HF?
Hydrogen bond.
Okay, you're going to discuss about hydrogen bonding. Okay, good. Okay, so we discussed about HF, okay, hydrogen bond, and you mentioned about polarity. Yeah, just now, someone mentioned about polarity just now. I think Wilson or what? Okay, he mentioned about polarity. Now, talking about polarity, how do you relate to this increase over here? So if you have all these polar molecules, what are the intermolecular forces of attraction exist over there? Michelle, if polar molecules, okay, what kind of intermolecular forces that exist for HCl, HBr, and HI?
Permanent.
Permanent dipole-dipole, okay,
Yeah.
permanent dipole-dipole. Now, when we look at permanent dipole-dipole, let's see whether the permanent dipole-dipole is able to explain the increase of the boiling point. Okay, so if you look at the group 17 here, because this one is all group 17. Okay, so if you have fluorine, chlorine, bromine, and then iodine over there. Okay, now I know going down the group, electronegativity increases or decreases, Megan?
Increases.
It's supposed to be decreases, Megan. Okay, electronegativity is supposed to decrease going down the group. Okay, why? I think you remember that even though the proton number is increasing, the distance and the shielding, okay, will outweigh the increase of the number of proton. So the attraction of the nucleus, the nuclear attraction will not be that strong. Okay, they won't have enough ability to pull the electrons. Okay, so it means when we look at it in permanent dipole-dipole, okay, what I can say is, okay, the HF and then HCl, HBr, HI. If you go down, then it's getting less electronegative. Okay, less electronegative means the permanent dipole-dipole is kind of PDD is kind of decreasing. Okay, I hope you understand. Yeah, so it's going to be because of the electronegativity, the PDD, permanent dipole-dipole, is kind of decreasing. So does it actually enough to show that there is some kind of slight increase of the boiling point? The answer is definitely no. It's not enough. So what we need to discuss is, okay, about VDW. Even though you mentioned there are two types of forces existing for these molecules, okay, these polar molecules, the VDW, okay, will explain that the size, okay, is actually increasing. When you go down the group, yes, okay, the H remains the same, but the size of this, they are getting bigger and bigger. When they get bigger and bigger, okay, what happens? Okay, your van der Waals forces increases. Okay, so generally the size increases. When size increases, we say the electron number of electron increases. Okay, so we can say the boiling point increases. So in summary, how do I explain in 3 points? Okay, I will say that, okay, number one, okay, my boiling point for HF is the highest, and then the boiling point for HCl, HBr, HI increases, okay, in trend. So that will actually give me my first point. Okay, my first point. My second point, okay, is going to tell why the boiling point of HF is the highest. Okay, so that actually we have to refer to, okay, HF has hydrogen bonding with another HF, with other HF molecules. The rest, okay, the rest you need to mention they have HF has strong hydrogen bonding, okay, with HF molecules. The rest have weaker PDD and van der Waals forces. You want to actually include they have a strong hydrogen bonding plus VDW also there. It's okay. Okay, so they have weaker PDD and VDW forces. You can mention. Okay, that's going to give you the second point. So the third point, okay, since I mentioned about HF, okay, all done. The third point, you mentioned why there is an increase. Okay, so here is going to be the increase of boiling point, okay, from HCl to HI is caused by increase in VDW, not PDD, yeah, increase in VDW because of increase in size, which is going to lead to increase in number of electron. Okay, that gives you the boiling point, which is higher. Okay, please put it in your own words. Okay, so that will be actually 3 points, okay, that we discussed about this graph. Okay, let's actually put it in a, let's say we don't have HF, we have another graph. Okay, this is going to be enthalpy change of vaporization. It means to vaporize something. Okay, so it's similar like a boiling point. If you have water molecules, okay, when they are in liquid form, if I change them, water molecules, to become gas, so that is going to be enthalpy of vaporization. Yeah, so energy required to change them into vapor. Okay, so Nathan, can you actually put it in points, okay, like what we have discussed just now? If I give you 3 points over here, 3 marks for this, what are the things that you will discuss over here, Nathan?
The one going down a group and also the types of forces.
Okay, so please actually give me point number 1.
H2O has a hydrogen bonding.
Okay, so okay, so that's going to be your second point. Yeah, H2O has stronger hydrogen bonding.
Oh, the first one is the trend.
Okay, so tell H2O has the highest enthalpy. Okay, enthalpy means energy. Yeah, so H2O has highest enthalpy of vaporization. Then from H2S to H2TE, okay, there's a increase in trend. So you mentioned about the trend. Okay, so point number 2, H2O has stronger hydrogen bonding. If you want to mention VDW, you go ahead. But H2S, H2SE, H2TE, let's actually discuss about them. Okay, just now we mentioned about polarity. Wilson mentioned about polarity. So maybe we get Wilson again. Wilson, is these molecules polar or non-polar?
Polar.
Yeah, they are polar because of,
Their shape is bent.
yeah, the shape is bent. Okay, because there are this one are all from group 16. Okay, oxygen, sulfur, selenium, tellurium, 6 valence electrons. So if I want to actually draw for SEs, so you will have something like this. So a bent shape is going to be there. Okay, so there is going to be presence of lone pair. So generally all of them are polar. So we are talking about they only have PDD and van der Waals forces. Okay. So now we need to explain, okay, why there is actually increase over here from here to here. So how do we explain? Number 3, maybe Kevin, can you tell me what will be the point number 3? Kevin, hurry up.
The size is increasing.
Yeah, so it's increasing. So
The
why?
There's are increasing electrons.
Okay, so VDW is increasing. Why VDW is increasing?
Because the electron also increasing.
Okay, so the size of the going down the group size is increasing. Okay, the size increases. That will actually make the electron to be more. Okay, so that will actually have you need more energy to break the intermolecular forces. So please explain all this. So that will actually give you the 3 points. Okay, 3 points. So now what happens if they give you this graph? Now, just now when we discuss about HF, okay, the first graph was about HF, okay. So imagine this is going to be your graph number 1. Just now we discussed about graph number 2. If I give you another graph, definitely got to do with ammonia. So graph number 3, okay. Similar, ammonia is group 15. So they have one lone pair electron. So the rest of this, PH3, ASH3, and then SPH3, they are all polar. So whatever it is, okay, when you look at these 3 components over here, the increase over here is caused by the VDW, even though they are polar. And if you look at this, they are high because of hydrogen bonding. Okay, and why this one is the lowest? Okay, maybe someone can help me to explain this. Benedict, why this one is lowest? CH4.
Because it only consists of van der Waals.
Yes, okay, because they are non-polar molecule. All of them are non-polar. You can see group 14 non-polar. So they have only van der Waals forces of attraction. But you can see a general trend which is going to be increasing. Why? Because going down the group, okay, size increases, van der Waals forces increases. Now, when you put all these together, okay, how many marks that we are looking about? Okay, you can see this is going to be, if I put it as this one, take note properly, yeah. So if I actually put, I give you 1 mark, okay, for all these 3. So you mentioned about van der Waals forces, all increase and so on. I give you 1 mark. And saying that, okay, these 3, they have highest among the graph, okay, so you will get another 1 mark because they have the hydrogen bonding. If you mention about this non-polar van der Waals forces, then after that the trend is going to be going up, van der Waals is going to increase and so on. You are going to get another 1 mark. Okay, but imagine for this question, I'm going to give you 5 marks. Okay, imagine I'm going to give you 5 marks for this question to discuss this graph. You can see there are 3 points over there that you can discuss, but it's not enough, okay, to discuss completely or to get the 5 points. So we need to actually talk about another 2 more points. Okay, so I want you guys to think, okay, Sharon, what can you say about the remaining 2 points that you need to include to get the full mark? Think.
The bond length.
Bond length. Now, do remember, we are not going to talk about bond length because, okay, you only talk about the bond length if you want to break hydrogen and F. You want to break and then you want to form H2 and F2. Then we talk about bond length. Okay, we talk about bond energy. Okay, but now we are not going to talk about that. Okay, because we are just trying to break the bond between molecules and molecules. So no need to actually mention about the bond length. Okay, no need to mention about bond energy. Here, what you need to mention over here is why H2O is at the top. Okay, I think one of the point, I think why these 3 at the top, why this one at the bottom. Okay, that's another one more point. Why? Okay, I think everyone knows the answer. H2O, HF, and ammonia, okay, they have hydrogen bonding. So they are at the top. CH4, okay, no hydrogen bonding. So they only have van der Waals forces. They are at the bottom. So that's going to be another one more mark. Okay, you're comparing. Now, where is another one more mark? Okay, that is actually what I want you guys to think. Michael, where do you think the another one more mark will come from?
How about the difference between
The difference between?
like how steep the increase of boiling point?
You mean from here to here?
Like the difference between, for example, CH4 going to SiH4, like it's steeper.
Oh, no need actually. No need. When you see here, it's like a general increase. Okay, it's just a general increase. So you no need to mention about that. Why steeper also, you won't even have enough points to mention about that. Unless SiH4 is like from CH4, then they become like this, way up, then after that they come down, then it's different. You can mention about that. But this one, no, since it's going up generally, so you no need to mention about that. What I give you a clue. Okay, I give you a clue. Why this graph 2, graph 1, and graph 3 is arranged like that? Okay, so here you see it. I know that hydrogen bonding is the bonding between hydrogen. Okay, H2O. Yeah, Giuliano, you're correct. Okay, I'll get into that. Okay, hydrogen bonding happens between hydrogen with NOF. Okay, so this hydrogen bonding between H and OF, okay, happens because, yeah, when you look at this, okay, fluorine is going to be the most electronegative element in your periodic table, and then hydrogen is the least electronegative element in your periodic table. Okay, so generally if I have let's say a graph and I put this one is boiling point and then I don't label anything in the x-axis, I want to show them, let's say for example H and N, so I have ammonia. H and O, I have water. H and F, I have HF. So I want to actually look at these 3 molecules and I want to predict their hydrogen bonding, and then I want to predict what will be the boiling point. So if I look at it, okay, H and F, okay, H and F, they have kind of the difference is really great, okay, because the least electronegative and the most electronegative, I will expect HF to be having the highest boiling point. Okay, and I will expect the water to be the lower than that. And I will expect, okay, ammonia to be way lower than that. Why? Because I think when you look at the electronegativity, it's supposed to be like that. Okay. But when you look at this graph, okay, HF, water and ammonia, do you have HF, water and ammonia arrangement? Do you have that, Josh? It's the different arrangement, right? Water comes first, followed by HF, then ammonia. So something is wrong over there, where there is another one more point. Okay.
They're in a different order.
They are in a different order, definitely. They are in a different order. So you need to actually find out or explain why. Okay, to explain that, I'm going to explain to you now. Okay, it's about the number of hydrogen bonding that they can actually form. Okay, let's actually look at water. Okay, water, they can actually have something, this kind of structure. So this one, I will put it like this so that easier to see. Okay, the lone pair. This is delta negative, delta negative. Okay, this one is going to be delta positive, delta positive. Now, if I want to actually put in form of, let's say, how many delta negative and how many delta positive, for example. So if let's say I want to find out, okay, how many delta positive, how many delta negative, okay. So how many delta positive? I have 2, okay. And then how many delta negative? I have 2. Now, I would like to actually put it in like this. The ratio is going to be the same, 2 to 2. Why I'm putting like the ratio is the same? Okay, it's like this. If imagine you are going to a party. Okay, you're going to party, and then imagine the delta positive guys. Okay, number of guys, and then the delta negative is going to be number of girls. Okay, the ratio is going to be 1 to 1. It means, let's say in a party of 30 people, okay, you are going to have how many guys, how many girls? Michelle.
In a party of 3 people?
30.
30? 15 guys, 15 girls.
Yes, good. 15 guys, 15 girls. Now, if they want to couple up or pair up, okay, each one guy will get one girl. Okay, each one guy will get one girl. So it means that everyone, okay, will have the chances to pair up. Okay, it means that if I have water, they can form hydrogen bonding with another H plus over here. They will actually form hydrogen bonding with another H plus over here. I'm not drawing everything. They will have hydrogen bonding with another lone pair over here. You will have like this. So it means they will actually form the maximum hydrogen bonding it can form. Now, but does it mean, okay, does it mean that each one molecule is having 4 hydrogen bonding? Not really. Okay, if you look over here, if you define hydrogen bonding is going to be between guys and girl. Okay, it should be, let's say, imagine this one is going to be, I refer delta positive as guy. Okay, this is delta positive. Okay, is these two is considered to be the hydrogen bond that is responsible for this molecule. Then Mr. Gopi, how about the remaining 2? Now the remaining 2 will be the hydrogen bonding responsible for this molecule. This one responsible for this molecule. Okay, so it means that, okay, the hydrogen bonding that you can form, okay, is actually like either from something like the ears of the Mickey Mouse over here. You can see something like this. Okay, the ears of Mickey Mouse to this over here, 1, and then like this, 1. So it means that hydrogen bonding, even though they can form the maximum number of hydrogen bonding, it means the number of hydrogen bonding that one molecule of water will be, okay, 2. 2 hydrogen bonding per molecule. And that's the maximum, okay, bonding per molecule. If we look at it in, let's say, how about ammonia? Okay, let's actually look at ammonia. Delta positive, delta positive, delta positive, delta negative. I just put like this, delta negative. So now, okay, if I have this, okay, it's very important to actually write down like this. I think much more easier to understand. Okay, so how many delta negative, how many delta positive? Okay, So you will have 3 delta positive and 1 delta negative. Okay, imagine now if you go to party, I think no need to give a number. Okay, maybe you have one guy, okay, one guy, and then 3 girls. Okay, so if there is a possibility of them getting partnering up or being couple, so what happens, this one guy will go and partner with one of the girl. Okay, so what happens is the remaining 2 girls, okay, they will not be participating in the partnering. Yeah, they are not going to get coupled up. So it means that there will be extra 2, okay, that will go into waste, or they are not going to be used up. Okay, they are not going to be used up because of lack of guys or lack of delta negative. Okay, so what happens, okay, even though they can form, okay, with another like this, okay, I'll just draw, even though they can form like this, but in reality, okay, it doesn't work that way because lack of delta negative. Okay, so it means this one, if I partner with this, what happens over here is, okay, the remaining 3 delta positive, the remaining 2 delta positive will go into waste. It means that this one will not get into bonding. This one will not get into bonding. Not enough. Okay, not enough. So what happens here? Do we actually get these 2 into bonding? Definitely no, not enough. So in total, how many bonding that do you have? You can see that from this diagram, there's some kind of one and another one. Okay, there is some kind of one and another one. And I told you, if you are partnering with delta negative and delta positive, you just stick to one. Okay, so here you see delta negative to delta positive, and this one will belong to this molecule. Okay, so how many total hydrogen bonding that you can have for ammonia is for one molecule is only one. Okay, it's only one. So it means, okay, in this ammonia, ammonia can only form one hydrogen bonding per molecule. The remaining, okay, will go into waste. 2 hydrogen bonding per molecule, 1 hydrogen bonding per molecule. Okay, let's go for HF. I know the confusion for HF will be a lot. Okay, why? Fluorine is going to be group 17, so you will have something like this. 3 lone pair. So this one delta negative, delta negative, delta negative, delta positive. You know what is the common thing that students will do? Okay, they know that this one, okay, will join with another HF. Delta negative, delta positive, 1. So this one will join with HF, delta positive, delta negative, another 1. This one will join with HF, another 1. This one will join with another HF. So is the answer 4? No, it doesn't work that way. Okay, you use the same thing just now. How many delta negative, how many delta positive? Okay, so here, okay, there are 3 delta negative and then 1 delta positive. So if just now we are talking about 1 guy and 3 girls, okay, now you have 3 guys and only 1 girl. Okay, 3 guy and only 1 girl. So what happens over here? Okay, there will be some of it will be wasted. The 2 guys will be wasted. Only 1 guy and 1 girl will form a bond. Okay, that's going to be, there will be additional 2 delta negative not being used. It means 2 lone pair, okay, will go into waste. Okay, it means ignore this, ignore this. Okay, so how many bonds that they can form? This one and this one. Out of this, one molecule will have how many bonds? So you follow negative and positive only. So this one is 1. So how about this? This one belongs to this molecule. Okay, so how many hydrogen bonds that HF can form? Okay, HF can only form one hydrogen bond per molecule. So in summary, okay, what are we going to have over here? In summary, based on this, okay, based on this explanation, in summary, if you have HF, if you have NH3, if you have water, okay, water will have two hydrogen bond per molecule. Ammonia and HF, they will only have one hydrogen bond per molecule. Okay, one hydrogen bond per molecule. So that actually makes, okay, the difference in the number of hydrogen bond, that makes a big difference. So if I actually put it in form of like this, okay, I know that this one contains two hydrogen bond, contains one hydrogen bond, contains one hydrogen bond. What happens? This one will override the HF, okay. So they will actually go higher than HF. So water will come over here because two bonding pair. So I will erase this part. And okay, and ammonia and HF, since they are 1 and 1, and then difference of the electronegativity is still there. Okay, F will be more electronegative. So they will actually still follow this sequence, which is HF is stronger than the hydrogen bonding is stronger than ammonia. Okay, even though they have one hydrogen bonding. But water, on the other hand, okay, because they have two hydrogen bond, okay, more hydrogen bond over there, they will actually give rise to stronger hydrogen bonding. So if we want to look at it in terms of the, let's say, coming back to this question, okay, so it will actually match, okay, what we have discussed, okay, which is going to be, you can see that, okay, the water is going to be highest compared to HF, and then ammonia is going to be the lowest. So what is going to be the another point? The another point is, okay, water forms two hydrogen bond per molecule. Okay, therefore they are the highest. Compared to HF and ammonia, they individually they actually form one hydrogen bond. Okay, but HF has a stronger hydrogen bond because of the stronger electronegativity of F. Therefore, the sequence will follow this. So that actually explains about the 5 points. I hope you remember this. Okay. In summary, what I want you guys to know, if you do not know how to explain, still fine. Okay. If you still do not know how to explain, I want you to memorize this, okay, where water can actually form two hydrogen bond, HF and ammonia, each molecule can form one hydrogen bond only. Yeah. So please actually remember this. Now, next, okay, there are some parts, okay, that you need to memorize.